I'll show the steps of construction of a 100,000 microfarad 200 volt capacitor bank. We'll do some experiments with high current discharge effects, maybe some magnetic effects. Should be a lot of fun, so if you got your seat belts, strap yourselves in. You might need to. We're going to have some fun with this video, and we're going to have some fun with our capacitor bank, and the next scene you'll see is going to be the beginning of construction. So fasten your seat belts and hold on tight. The first step in construction, of course, is to get the raw materials together. The capacitors are going to be mounted on a wooden base. I'm not sure if this is enough wood to mount all of the capacitors, but this is an old shelf that we're getting ready to discard, and it'll be broken down into two boards that'll be glued side by side, along with the lighter colored board on the right. That'll form the base, and it should probably hold at least 60 of them, maybe all 100 of them. Now we have the capacitors. This is about 106 of them or 107 of them. These will be the guests of honor. I have one standing up. We'll zoom in on it and get a good look at it. Have to get a little closer. Let's see if we can read it. Okay, there we go. 200 volt, 1,000 microfarads. Each one will be pre-tested before it's mounted on the board, and we'll have about 100 of them all together. If the boards that I chose don't hold all of them, we'll just glue more wood to it. But it'll be 100 of these babies. And this box is only stacked, you're seeing the top layer, it's actually 2 layers high. I've separated the shelf boards and laid them out flat and put the other board next to it and glued them together. I have a resulting board now that measures approximately 10 by 24 inches. And of course that'll be the mounting base for the capacitor bank. And next I'm going to size it and calculate the total number of capacitors that it'll hold. My resulting 10 by 24 inch board holds 6 capacitors wide by 15 deep capacitors. What I'll have to do is cut off this tail extension left over and glue a 4 by 10 across the back. So that'll be my next step. 4 by 10 will hold 102 capacitors, and I'll just put 100 on it and leave a little bit of space on there. But it's moving along pretty fast, and it's looking good. I leave enough space between the capacitors to where after the bus bars are wired in, I'll still be able to remove a capacitor as I need to for replacement. Each capacitor will be held in by 1 drop of silicone glue. That'll hold the capacitors firmly in place, and at the same time it'll still make it feasible to just pop one loose anytime I need to, because the silicone will break loose and yet it'll hold firmly. So that's what it looks like. So far 6 by 15. Glue the extension across the back. There'll be enough room for 102, and we'll put 100 on it and wire it up. I've trimmed off my tailpiece and glued on the 4 by 10 tail extension. I now have a 10 by 27 3/8. That's enough to hold a total of 102 capacitors, and we're going to leave 2 of them off. Now before I mount these capacitors, like I said before, I was going to be using the silicone rubber glue, the GE household silicone, and they're kind of hard to break loose after you do that. You got to push it pretty far to the side, and once they're wired, the bus wiring won't permit it to move very far. So what I'll have to do is test each capacitor first. So here we have a schematic of the charge-discharge box. Now what that does is it allows me to charge a capacitor, and regardless of how big it is, By using a series ballast lamp, I can control the charge current and keep it down to a safe value. Even a single capacitor would draw in excess of 100 amps at least for a pulse. While it's charging, it could destroy the bridge rectifier. So to avoid that, we use a ballast lamp in series, and we're using a center off switch, so we can take the center contacts and wire those to the capacitor and ballast arrangement, and we can select charging from the bridge rectifier, or we can also do it by using a short, since the bulb is in series all the time. Now up here is part of the parts inventory we'll use to construct the charge-discharge box. Have an AC power cord, a CEE input receptacle, bridge rectifier. We're using a speaker terminal block. We're using it for the output connection, and the ballast lamp, and you see the project box behind everything else, and of course the center off switch. And we'll be using wire from this roll to wire the charge-discharge box. So that's it for this part of the construction. Next up, what we'll do is we'll show the charge-discharge box being used to test capacitors. I'll use a 60-watt bulb for an individual capacitor and probably about a 300-watt bulb for the whole capacitor bank. This is the interior of the capacitor charge-discharge box. I thought I'd go ahead and show it while I could. Now, excuse me there, I bumped the switch on the camera. Now on the right hand side you see the power wiring coming up from the CEE connector going into the bridge rectifier right over here. And comes out on the orange and gray wire to the double pole double throw switch. Okay, in the position facing the output terminal strip, the bridge rectifier is connected to the capacitor and ballast, and in the position in the center, it's neutral or disconnected from the capacitors, neither charging or discharging. And of course that's the position you use when you get the capacitors ready to fire. And then when you pull the switch all the way back, you get this little short circuit wire, and it discharges the capacitor through the safety ballast. So you can always be assured that your capacitor will be fully discharged before you handle the connections. And using a double throw switch, we always isolate it from the power line anytime it's in a position other than charge. It's fully isolated from the line for safety. So next I'll assemble the cover and demonstrate a test of the capacitor by charging, discharging, and then allowing the capacitor to stand charged and test for leakage. Now the charge-discharge box and the capacitor are connected along with the ballast lamp and a voltmeter. And what we're going to do is we'll charge the capacitor, and you'll notice the light come on brightly for only an instant, and then as the current falls off it dims. So it charges very fast. Now if you'll observe, normal line voltage at the house is about 118, but the capacitor has charged up to almost 170 volts. And the reason for that is that it charges to the peak value of the sine wave, which is about 1.414, or the square root of 2 times the average voltage. So you get almost 170 volts when you rectify it and charge a capacitor with it. Now the neutral position of the switch, or the center position, will disconnect the capacitor, and you'll notice the last digit on the volt reading will go down slowly as it discharges very slowly through the meter. Now when I pull the switch all the way back, it'll blink only brightly for a second because it'll discharge through the bulb like that, and it's all gone in a second. And of course a short would probably do in excess of 200 amps and make a loud pop, and it would be gone. But the bulb limits the current to a little over half an amp, and you have no sparks and no burning of contact surfaces. And also, anytime you discharge a capacitor, especially an electrolytic, into a short, you run the risk of it exploding. Okay, we're charged, coasting, discharge. And that's it for the charge discharge. Now we can charge the capacitor like this. And now once the capacitor has been charged, we can put it in the coast position or neutral on the switch. Now carefully disconnect the capacitor and the meter to avoid a short circuit. Now if we let it stand for about a minute, and carefully disconnect the positive side, now let it stay fully charged for approximately a minute. A little over a minute has passed. I did not make a note of what the voltage was before I started, or as I started. But if it's still above about 165 volts, it indicates that the capacitor has very low leakage. And we're about 163 volts. So the capacitor has been self-discharging to a degree, but pretty slowly. This is a good capacitor. Now, if I were outdoors on the ground, I would not make this connection with the power applied, even though we do have the switch being double pole isolated from the line. I believe in having two modes of isolation or safety, and just relying on the switch as one. Outdoors, I would unplug the line cord and have the switch in neutral. Now I'll discharge the capacitor pretty quickly. And that concludes the demonstration of how the charge-discharge box works and how to test the capacitor. At this point, all 107 capacitors have been tested. We did the charge test, the discharge test, and then the 1-minute standing leakage test, and found all 107 of them to be good. Next, I'll clean the bottom of each capacitor, and I'll clean the top of the wooden base with alcohol, and then I'll use the silicone household glue to start mounting the capacitors. So this next step, of course, is purely mechanical. Got us a good look at the capacitor charge-discharge box again. We'll go around here to the back. See the detail of the incoming AC power connector and the outgoing DC output connector, which of course the discharge path also comes through here. So the next scene will probably be all 100 capacitors mounted.